Okay, welcome back to another video lecture for Math 1316, Plane Trigonometry. And in this video lecture we're covering topic 1.4, and 1.4 is going to be using the definitions of trigonometric functions to derive the reciprocal identities and the signs SIGN and range of function values, as well as the Pythagorean identities and the quotient identities. Okay, recalling from section 1.3 the definitions of our 6 trigonometric ratios, we have sine, cosine, and tangent that are all ratios of different sides of a right triangle to each other. And all of these are done with reference to a right triangle whose angle A is in standard position on the coordinate grid, this being the angle that we're interested in. And the naming scheme is that A goes across from A, C goes across from C, B goes across from B. And very quickly I wanted to show an alternative method for remembering where the lowercase letters go on a triangle. Of course, remember the right angle is always capital C, the angle in standard position is always capital A, and the other angle is always capital B. So another way that you can remember where each lowercase letter goes is if you look along any particular line. For example, this hypotenuse here. It has capital A and capital B on the endpoints. The only thing that is missing from triangle ABC is missing C, so we put a lowercase c in the middle. If you look at this line segment from B to C, it has B on one endpoint, C on the other, so the only thing it is missing is lowercase a, and that's how we know that this side is lowercase a. And lastly, this is capital A and capital C as the endpoints, so we know it's missing lowercase b in the middle. It's just an alternate way to remember the labeling of a triangle if the A across from A, B across from B, C across from C thing does not work for you. Okay, so we already discussed how each of the trig ratios, each of the 3 basic ones, sine, cosine, and tangent, they are related to another trig ratio, which is just the ratio in reversed order. So if sine is A over C, what if we had chosen to give that ratio in reverse order, C over A? We define this to be the cosecant of A. If we have cosine, which is the ratio of B to C, then we have the secant, which is just the reversed ratio, that is C over B. And if we have the tangent of A, that's defined to be A over B, then the reversed ratio, B over A, is the cotangent. Now from this we can actually write a set of identities, which is a way to translate between each of these types of trig ratios. And we can do that fairly easily just by noticing the relationship of sine and cosecant. Well, if sine of A is A over C, and cosecant of A is C over A, then the effect that multiplying these 2 ratios has is to reduce everything down to 1. So if you take the sine of A and then the cosecant of A and you multiply them, it gives you 1. To write this using the actual trig ratios as opposed to the fractions, that's sine of A times cosecant of A equals to 1. Now notice here that we have an identity. Anytime you take the sine of something times the cosecant of the exact same something, it's going to make 1. And this is one of the identities that we call a product identity. And we could write one of these for each of the other trig ratios. For example, cosine times secant will be 1, and tangent times cotangent will be 1, provided that they are all referencing the exact same angle. Now, if I were to divide both sides of this expression by cosecant, then what I would get is that the sine of A is just equal to 1 over the cosecant of A. In other words, if I have a sine and it is advantageous for me to do so, I can choose to take sine out of there and write it as cosecant. Now, that is probably not an advantageous thing to write unless we're in maybe a more advanced course where those things pop up a little bit more often. So really the other way around is probably the more advantageous thing to write. if I were to divide both sides of this expression by sine, then we'll get that the cosecant of A is just 1 over the sine of A. And the reason why this is important is because sine and cosine and tangent we're exposed to as early as geometry. So we're a little bit more used to dealing with sines and cosines, maybe not as used to dealing with tangents, but we're at least used to dealing with sines and cosines from a very early time. So what that means is when we see something like cosecant, secant, or cotangent, instead of dealing with cosecant and secant, which might require us to do a little bit more thought process on what the actual ratio is, we can simply figure out what the sine is, which is significantly easier, and then we can just flip it over. And that should make sense because that's right in line with what we did to define these ratios in the first place in section 1.3. Okay, so of course we can play this game here to create a list of identities. You know, we have that the sine of A is equal to 1 over the cosecant of A, and that the cosecant of A is equal to 1 over the sine of A. We can play a similar game with any pair of the trig ratios on our little cheat sheet note card thing from section 1.3. So the cosine is B over C. If you were to multiply that by the secant, which is C over B, everything cancels out and goes down to 1. So notice that B over C is the cosine of A, and C over B is the secant of A. So cosine times secant gives us 1. And of course, we can repeat the exact same moves we did with sine to derive the ratios for this. If you divide everything by secant, then we'll have that cosine of A is 1 over secant of A. And if you divide everything by cosine, then instead we have that secant of A is equal to 1 over cosine of A. So there's two more reciprocal identities that we have that give the relationship between two trig ratios. So once again, that is that the cosine of A is equal to the 1 over secant of A, and that the secant of A is equal to 1 over the cosine of A. Now the next two identities are given without any deriving, and that is that the tangent of A is equal to 1 over the cotangent of A, and vice versa, the cotangent of A is equal to 1 over tangent of A. And what you notice is that these follow a pattern. All the reciprocal identities do that. Now if you wanted to write these in their product form, which is actually when we get to the section that covers the majority of the identities, we'll discover a way to remember all of these identities. Right now, it's worth having these on a note card somewhere so that you can reference them. And these are always given to you on your pink sheet, which is the trig identity list. Now, later on, we'll discuss which of these identities must be memorized. And then there are some of these that you can reference back to the identity sheet and look up and do them that way. But in general, there are some of these identities that you must memorize. For example, I would say the sine of A, the cosine of A, and the tangent of A are worth memorizing. Because if you have those memorized, then you can use them to derive all of the other identities in this list. Okay. Now, it's also worth noting before going forward here that we do have another identity for tangent and cotangent. So recall that the tangent of A from section 1.3 is the sine of A over the cosine of A, and that the cotangent of A is the cosine of A over the sine of A. This just gives us a very long list of ways to take ratios that we think are difficult and to put them in terms of sines and cosines. So that's actually one of the strategies which is worth noting from section 1.4. It's kind of just thrown in there, but I think it's an extremely important strategy, especially when we get to things like proofs. If you have the ability to take trig ratios and to express them as sines and cosines, well then notice that that means that your memorization is reduced really to a list of 2 for how to handle the specific trig ratios. Now, is this always the easiest way? No, but it does always work to put them in terms of sines and cosines. The other thing is that if you can put a big expression with trig ratios in it into terms of sines and cosines, usually what that will do is it will reduce that ratio to something that's a little easier to handle through another identity, which we can reference off of the pink sheet or we might have memorized a little bit later on. Okay, so as an example here of how these identities get used, suppose we wanted to find the tangent of theta, given that the cotangent of theta is equal to 4, and then we'd like to give a description of what triangle this particular trig ratio is telling us about. So first of all, we can notice that the tangent of theta is just 1 over the cotangent of theta. So if the cotangent is 4, then that will give us that the tangent of theta is just 1 over 4, and that is the appropriate answer. Now it does also ask us what triangle does this describe. So we draw ourselves a right triangle, A being the angle in standard position, C being the right angle, B being the other one. That means C is here, A is here, B is here. And we can recall from our definition for tangent that tangent is just A over B. So A is this guy right here. It's the top number in our fraction, A equals to 1, and B is the bottom number in our fraction, B is equal to 4. Now, of course, we can do Pythagoras here. We can do Pythagoras here in order to figure out what the missing side length C is. So 4 squared plus 1 squared will give us the square of C. So that is 16 plus 1, which is equal to 17. And so, of course, the missing side length is the square root of that particular number if we were to square root both sides. So the square root of 17 is equal to C. Now notice that if we were asked to produce any other trig identity, any other trig value out of this triangle, we can now do so. We know that the sine will be A over C, that the cosine will be B over C, and that the tangent was already given to us, so we can now assemble our list of 6 trig ratios out of this triangle. Another thing I wanted to point out here is that notice that with any one trig ratio, we can show all the information about a triangle, a right triangle, in standard position if we know what that trig ratio is. Now, we could have also done this from the definition of cotangent because this one was not particularly difficult. Recall that it is B over A. So 4 over nothing is like 4 over 1. If we wrote that as a fraction, that means that the B is equal to 4 and the A is equal to 1. And you notice that it agrees regardless of what way we choose to look at this. Now the next example is very similar to the previous one. Again, it asks us for a trig ratio given a different trig ratio, and then we want to describe the triangle that this trig ratio is telling us about. So first of all, we have that cosine of theta is equal to negative square root of 20 over 10, and of course we know from our list of reciprocal identities that the secant of theta is just 1 over the cosine of theta. So that means that the secant of theta will be equal to 1 over this fraction here, which is negative square root 20 over 10. Now this is a compound fraction, which means that we will have to simplify this into a single fraction. This is like 1 over and then another fraction. So from college algebra, that is keep the top number the way that it is, change the sign from divide to multiply, and then flip over the bottom fraction. So that is negative 10 over square root of 20 is equal to secant of theta. Now also note here that we are not allowed to leave a radical on the denominator side of the fraction, so we have to go through our rationalization procedure for this. And if we were to do that, what we will get, the hack for that was that the denominator is just whatever was inside of the radical to begin with, and then we multiply the numerator times the denominator and reduce the fraction from there. So that is negative 10 roots of 20 over 20. Now notice that negative 10 over 20 is a reducible fraction. It's negative 1/2. So what I can do is reduce the top and bottom to this thing right here. Okay, so that is negative root 20 over 2. All right. Now, when we have a cosine ratio or a sine ratio or a tangent ratio which is negative, there are a few things that we need to note here. On a coordinate grid, how do we tell what direction the triangle is being drawn in? Now we know that there's a negative side somewhere in here. So the secant is negative root 20 over 2. And if we wanted to draw a triangle here in standard position where this is A, this is C, and this is B, I need to move my camera down just a little bit. Sorry. Okay, so if we wanted to draw this triangle, what we're going to notice is that the secant ratio is defined as C over B. Well, C, the hypotenuse side, can never ever be negative. So C has to be positive square root of 20, which means that B has to be negative 2 in order for that to be negative root 20 over 2 when we put that ratio together. Now the problem here is we also have to decide what exactly that means. Now we know this is negative 2, but when we go through our motions with Pythagoras, what we're going to get is a positive result for this guy right here. Okay, so whenever we have negative trig ratios, there's a little bit of extra thought process that goes into this to decide where that trig ratio falls on the coordinate grid, and that is the next part of 1.4. Okay, now here we have a coordinate grid, and we notice that we have positive numbers on the x in this direction, positive numbers on the y in this direction, negative numbers on the x, and negative numbers on the y in those directions. And so how do we handle positive and negative trig ratios? Well, the good thing is, if you remember quadrant 1, which is this quadrant right here, everything is positive. That means if this is always A, and then I have some point up in this quadrant B, and the right angle is always somewhere on the x-axis. I've drawn a couple of examples here. So B is like up here, or like B is there, or like B is there, or B is there. So anything in quadrant 1, notice that when I draw a right triangle, the b distance, lowercase b distance, has to be positive. Okay? Well, also notice that when we're in quadrant 1, then the lowercase a distance must also be positive. So that means that any of the 6 trig ratios that I put together are assembled out of positive a's and positive b's. All right, so what does that mean for us? Well, first of all, Pythagoras' theorem squares 2 numbers, adds them together, and then takes the square root of them. So what that tells us, because squaring a number always makes it positive, that tells us that c, lowercase c, is always positive regardless of what quadrant that c happens to be in. So if I have a triangle in quadrant 1, c is positive. Triangle in quadrant 2, c is positive. In 3, c is positive. In 4, c is positive. So the negativeness or positiveness of our trig ratios is solely determined by the a side and the b side, whether those are positive or those are negative. We'll notice that b is equal to the x distance, and that a is equal to the y distance. Furthermore, notice that every triangle from the earlier section 1.3 can be written with trig ratios, and that those trig ratios define all triangles which are similar to each other. So what that means is I can find like the lowest possible trig ratio, and it describes a range of all of the possible triangles that I could want to draw, just as the ratio of one side to the other. In other words, all similar triangles can be scaled up from something smaller. So just for argument's sake here, let's just set c equal to 1. Now we know c has to be positive, but let's set c equal to 1 just very quickly so that we can establish a few things here. Well, first of all, notice that if c is equal to 1, then both the sine and cosine ratio, sine of a and cosine of a, will be something over 1. In other words, sine just becomes a, and cosine just becomes b. Okay? So if cosine is b, then notice that cosine has the effect of describing the distance in the x direction. And if sine is a, then sine has the effect of describing the distance in the y direction. In other words, the y's are the sines, and the x's are the cosines. Now notice here that this gives us a very, very nice identity here. First of all, because this is a right triangle, I know that I can apply Pythagoras' theorem, which is a squared plus b squared equal to c squared. But c squared is just 1, because the only way to get 1 as our side on that, the hypotenuse side on that triangle, is to take the square root of 1. So that means that c squared must also be 1. Well, notice that if a, when we have a triangle set up this way, is just sine, then we can write down that sine squared of a plus cosine squared of a is just 1. And this is what we call Pythagoras' trig identity. It's one of the most important ones. Whenever you see sine squared plus cosine squared equal to 1, this is just a statement that is always true. If you take the sine of something and square it, plus the cosine of the same something and you square it, it will always equal to 1. Okay, so some reasons why that's important. Now notice that that will always be true anywhere in the coordinate plane, because the act of squaring sine, whether it is positive or negative, will just create positive sine squared, and the act of squaring cosine, regardless of whether it is positive or negative, will create positive cosine squared. So this hypotenuse will always be 1 somewhere in this coordinate grid this way. Okay, so how do we deal with negative trig ratios? Okay, in the previous example, we had that the secant of theta was negative root 20 over 2. Now, notice here that since secant is c over b, the c value had to be positive. So that meant that our hypotenuse side was positive and that the b value was negative. What I want to show you is that if the b value is negative, then we end up somewhere in one of these two quadrants, either quadrant 2 or quadrant 3, where this guy is root 20, this guy is root 20, and this is negative 2 worth of distance. So without some additional information or some boundary conditions, the answers about what triangle the secant of negative root 20 over 2 can describe, well, it could describe either of these two triangles. And just notice here that the only difference between these two triangles, which are congruent to each other, is that here we would have a positive a distance and here we would have a negative a distance, and that is it. But what's worth showing here is that the secant ratio is negative in both quadrant 2 and quadrant 3. We'll also notice that if the secant ratio is negative by association, since all you do to get a cosine is you flip over a secant, like if I just flip that fraction over, that's cosine, that means that the cosines are negative in these two quadrants as well. Okay, so what have we learned? Well, we've learned that secant and cosine are negative in both quadrant 2 and quadrant 3. Now, in quadrant 1, it should be no surprise. Quadrant 1 is the typical starting place of algebra 1, where everything is positive, and that's because we don't like to include negative numbers until we have a good grasp over the way that they move. It should be no surprise that all of the trig ratios in quadrant 1. Well, now think about what if we had had a sine or a cosecant that was negative. Okay, so if we look at positive or negative sine or cosecant, notice that sine is defined in terms of a. So if the c distance, which we've established, must always be positive because we get that from Pythagoras' theorem, and it squares numbers, which makes them positive. And the only option for a negative sine or a negative cosecant is for the a distance to be negative. Well, if the a distance is negative, then that means that it must fall either in this quadrant or this quadrant, because that's where the y coordinates are negative. And if you recall, the sine affects the y coordinate because it is the a distance, which is the distance in the y direction on the triangle that we draw. So that means that sine and cosecant are negative in the third and fourth quadrant. Okay, so then we have to discuss the tangent ratio, which is what are the slopes, so to speak. Now, notice that tangent is defined in terms of both a and b. So either a or b could be positive or negative. C is the only one that can never ever be negative. So if both a and b are positive, then obviously in quadrant 1, the tangent and cotangent ratio are also positive because everything is positive. Now, what about if we're in quadrant 2? Well, the a distance is positive in quadrant 2, but the b distance would be negative in quadrant 2. That's a mismatch of positive to negative, so a ratio of a positive over a negative or a negative over a positive will be negative. That means that tangent and cotangent are negative in the second quadrant. Now notice in the third quadrant that both the a distance, which is the y direction, and the b distance, which is the x direction, will be negative. So any ratio of negative over negative will produce a positive. That actually means that tangent and cotangent are both positive in the third quadrant. Now the only other place where they're mismatched is here in the fourth quadrant. And that is because the b distance is positive, but the a distance is negative in the fourth quadrant. So that means any ratio involving a to b will be either positive over negative or negative over positive. In other words, the tangent and cotangent ratios will be negative in the fourth quadrant. An easier way to remember this is that the sine and cosecant values are positive in the second quadrant and everything else is negative. The tangent, get rid of that parenthesis. Tangent and cotangent values are positive in the third quadrant and everything else is negative. And that the secant and cosine ratios are positive in the fourth quadrant and everything else is negative. And then everything is always positive in the first quadrant. This is kind of the first important list of things that we want to memorize with regard to trig ratios and whether they're positive or negative in the course. Okay, so at this point we have reviewed Pythagoras' identity, which is that sine squared plus cosine squared is equal to 1. We have reviewed the various different reciprocal identities, which is that cosecant of a is equal to 1 over sine of a, and so on and so forth. And we've also reviewed where the trig ratios can be positive and where they must be negative. Now, some of the questions in the homework will ask you to identify what quadrant something falls into based on two trig ratios. And I forgot to mention in this discussion here that the information about the positiveness and negativeness of two different trig ratios that are not related to each other. That means it can't be sine and cosecant. They're related to each other. It can't be secant and cosine because they're related to each other, or tangent and cotangent because they're related to each other. But if you have two different trig ratios and you have information about whether they're positive or negative, that will uniquely tell you what quadrant the triangle falls in. So from here, we will be looking at some specific applications of these types of trig ratios, and of course the homeworks will all ask you pretty much, it's going to be pretty exhaustive, but they're going to ask you to write the 6 trig ratios for a bunch of different situations. And this is really, really important, because if you do not know the way that sine, cosine, tangent are defined, and their multiplicative inverses are defined, then you really will not be able to do anything else in the course. So it's very, very important that we first of all memorize the definitions for sine, cosine, and tangent at a minimum, and we memorize which trig ratios are positive and in what quadrant they are. Furthermore, in Unit 1, which is sections 1.1 up to 1.4, we want to make sure that we have memorized the identities for tangent and cotangent, which is that it is sine of A over cosine of A, and cosine of A over sine of A for cotangent. Lastly, we do want to have in our mind what Pythagoras' theorem says, that is a squared plus b squared equal to c squared. We want that to be automatic. Anytime we need to find out what side C is, we can do Pythagoras with side A and side B to find side C. Now also, going forward here, we want to understand that sine squared plus cosine squared equals to 1, because the cosine ratio is somehow tied to the x's and the sine ratio is somehow tied to the y's. So it's a really long list, but those are kind of the really, really important points that we want to have memorized. The proofs are there to help us understand why these things must be true, but if you don't know how to prove the individual statements that we've used so far, that's fine, because this is sort of your first exposure to these concepts, and there's an entire unit on proofs later on into the course where we're going to talk about the techniques and all of that stuff. So the proofs are there to help you understand why. You do not need to know how to prove these statements yourself. You just need to have the results memorized. One last little thing, if you recall the reciprocal identities, there were some moments where I talked about the product version of those identities. That's probably the best thing to memorize, at least at first, because they're very, very easy. It's if you take a trig ratio times the reverse trig ratio, then it will equal to 1, and from that we can derive all of the other reciprocal identities. So that is very, very, very nice to have memorized. If you can do all of that, then you've got section 1.4.